Awesome. Here we go. Hello and welcome, everyone. My name is Nick Saldana. I am in grade 12, and this is my MCV for U1 STEAM project on biomedical engineering. I'm doing a video portion for the lesson so that you guys have an option if you'd like to maybe just read through it in my PowerPoint or if you'd like a little YouTube video on it. So what I have planned today is the following. I have four parts, as you guys have seen in my in my slides presentation, and I'm going to split it up into four over here so that you guys aren't sitting through 25-minute long videos of me talking. So if you guys feel more comfortable with derivative laws but are having a bit of trouble with optimization problems, you guys can skip right to the fourth video where I'll have optimization ready for you in it. And I'm going to try to keep every video to within 10 to 12 minutes long, so you guys aren't too bored. But yeah, other than that, let's get started. We're going to start off with part one, which is derivative laws. And as everyone knows, derivative laws are an important part of the calculus course because we use them for many applications. And before we move on to those applications, we got to get the basics down, which are realistically just these five derivative laws. There are more, but you're not going to be able to see those in high school, most likely in university. So let's get started with the power law. As you can see right here, the power law is the most common and most simple derivative law, and it involves having a function raised to an integer that is n. Essentially, what this means is that you have x to the 2, x to the 3, x to the 4, whatever, x to the negative 2, x to the negative 3, any number that is raised to. And the course of action here is to take that raised number right here, and you're going to want to move it to the front. So by moving it to the front, as you can see, this is the derivative. By moving it to the front, you have nx. So whatever the exponent was, you have it times x now, and you're gonna have to subtract one from the exponents. So whatever n was initially up here, you're gonna subtract one from it, and you're gonna have your derivative. Now let's take a look. Actually, I'll leave it in green. Let's take a look at some examples. So right here, we have h of x is equal to negative x squared plus 6x plus whatever that ugly number is. So the reason I chose a big number here is to kind of show you guys that when you have a constant number, you don't have to use a power law. There's no real use for constant numbers in derivatives, and they get canceled out. So this could be 2, this could be 3, this could be negative 49,205. Doesn't matter. It's going to be canceled out when you're taking the derivative. Next up, we're going to look at the first number value, which is negative 2x squared. So we know, as per the power law, that we move the 2 down and in front. So we did that right here. 2 goes down and in front, negative 2x. So now you might ask, what do we do with this 2 up top? So as you remember, we subtract 1 from the top. And negative 2x to the 1 is just negative 2x. So we're done with that value. Moving on to plus 6x. So again, everyone has to remember that there's an imaginary 1 right here above the x. When there's nothing there, you assume it's 1. So 6x to the 1, you bring the 1 down, as we've said. 1 times 6 is 6. 1 subtract 1, as you remember, you got to subtract 1 from the top. 1 subtract 1 is 0. So the x cancels out, but the 6 stays constant. And this is our final answer, negative 2x plus 6. Let's see. And I'm going to go through this next one a little bit quicker. We have p of x is equal to the square root of x. So this might be a little scary for some people if this is their first time dealing with derivatives, because there's no clear derivative shown. But we all remember back from, I think, grade 10 or grade 11 with the exponent laws and exponent review, that anytime you see a square root, I went into that. Oops. Anytime you see a square root that looks like this is always going to be equal to, always going to be equal to x raised to the 1/2. So you can try it with your calculator if you're unfamiliar, but that's the truth. And we use this to evaluate this. So instead of dealing with the scary square root symbol, I switched it right away to 1/2. So x to the 1/2. Again, you just follow the steps that we did in the first example. Move the 1/2 down to in front. 1/2 times x to the negative 1/2. And this might seem a little bit scary to some. No, don't fret though, because if you remember back to the exponent laws, anytime you have a negative exponent, negative 1/2, all you have to do is flip it over to the denominator. So it will be something like 1 over x to the 1/2. Get rid of the negative exponents, and we're all happy. So as you can see, that's what we did here. And I just converted it back to the square root because it just looks nicer instead of having a fraction in the exponents. Again, that's not needed, but something you can do. Yeah, that's power law for you. Moving on, let's get a different color for the highlighter. Let's go green. Oh no, we're already green. Okay, cool. Let's switch to red. Awesome. So product rule. We have product rule right here. And product rule is generally used when we have a function, a bigger function, p of x, that is comprised of two functions, two smaller functions being multiplied together. And essentially, the course of action here is to take the first function, which is f of x, and you take the derivative of that, often maybe using power law or one of the few others when you get into higher level derivative questions. You take the derivative of the first times the regular second plus the derivative of the second times the initial first. Again, it seems a little bit kind of up in the air right now, but we will get into some examples right here. So for the first example, we have p of x is equal to 3x subtract 5 times x squared plus 1. So we just follow the steps, take the derivative of the first. So the derivative of this would just be 3, as we have right here, times the regular second function. So if this is p of x, this is f of x, if that helps you guys. And oof, pardon my penmanship. And this is g of x. Oof, that's rough. Okay, so we take the derivative of the first times the regular second plus the derivative of the second. So derivative of x squared plus 1. We bring the 2 down, subtract the 1, just 2x, as we can see right here. And then you're multiplying it by the original first, which is 3x subtract 5. This right here is the hardest step. Once you've gotten past this step, it's kind of just like a grade 9, grade 10 question where you just got to expand the brackets and yeah, you order them in terms of descending variables, 2, 1, 0. And yeah, that's pretty much all you need to know for power law. This is another example. You guys can look through it, but I'm not going to because it's pretty similar to see what we have here. So moving on, we have, let's get another color. Purple. All right, we have quotient rule. So this is probably one of the harder derivative laws to take into account because of the simple fact that we're dealing with quotients. So we're dealing with division statements that are something divided by something. So as you can see here, the basic form of quotient rule is that if you get a function that is a smaller function divided by a smaller function, and it makes up h of x, to take the derivative of that, it's sort of similar to the product rule where you have the derivative of the first, so like derivative of f of x times g of x, but instead of adding as we're doing in product rule, right here, we're subtracting. So you're subtracting the derivative of g of x times f of x. Again, I don't know if I mentioned this, but the order of these two doesn't matter. So if you see it another way in a textbook or in your notes, that's perfectly fine. It's just the way I prefer to do it. And then this is all going to be divided over, g of x squared. So let's get into some examples. I know I found this pretty difficult to understand to begin with, but again, with practice, everything becomes a lot easier. So right here, we have q of t is equal to 2t subtract 3 divided by t plus 5. That's a mouthful. Whew. All right, so we have this function, and we know that we have to take the derivative of it, as you can see right here. So Let's go back to quotient law, remind ourselves that we have to take the derivative of the first times the second, subtract the derivative of the second times the first. So derivative of the first, so this derivative right here, this just turns into 2, because remember, there's an imaginary 1, bring it down, times 2. I'm sure we know that by now. Times the original second, which is just this one. Subtract, this is where a lot of people make mistakes because they're thinking in product rule terms, but we're always subtracting in quotient rule. So we're subtracting the derivative of the second, so t plus 5, this is a constant, so it gets canceled. T has a 1 right here, bring it down, 1 times t to the 1 subtract 1 is just 1. So you got 1 here, times 2t subtract 5, which is just the, that should be a 3. That's an error. Okay, well, you guys know for now. That's a little mistake, but yeah, that's supposed to be a little 3. Okay, so and this is all divided over t plus 5 squared, and that's just the bottom number squared. Awesome. And then once again, this kind of turns into a grade 10 or 11 question once you get past the first step, because you have all these values that you multiply together divided by t plus 5. So again, it's perfectly fine to leave it in this case right here, because this can't be simplified any further. This is a constant number over a binomial that's being squared. So no worries. That's the extent of that question. Same deal for this one. Again, I'm not going to go through it. Save you guys some time. Same deal. You're taking the derivative of the first times the regular second, subtract the derivative of the second times the regular first, all over the square, the second function squared. But yeah, awesome. And then you guys can see the work there, and we're moving on. Okay, what's next? We have chain rule. So chain rule and power of a function rule, they're kind of similar in the fact that they both deal with binomials, trinomials, getting expanded and being raised to some power. So let's get my highlighter out. Let's go red. Awesome. So chain rule, as you can see, is when we have a function in grade 11, or not even grade 11, grade 12 in advanced functions, we learned about composite functions, which is where two functions are combined. So it's f of g of x, and this would be written as f og. Kind of remembered it as fog for when I was studying for advanced functions, but yeah, that's f of g of x. When we're faced with this, what we have to do is take the derivative of f times whatever's in the bracket, so whatever g of x is, whatever's in the brackets, multiplied by the derivative of what's in the bracket. So let's look at an example. Again, examples make everything easier. So right here. Okay, so we have g of x is equal to 3x subtract 5, all being put to the 4th exponents. Awesome. So what we do now is we're going to move this down, just like power rule. Move it down to the front. And we have 4x, or 4 times 3x of 5 to the 3. And you remember we have to subtract 1. And right there, so we have 1. And we take the derivative of what's inside. Whatever's inside is just a 3, because this is a 1. 1 times 3 is 3. X to the 1 subtract 1 is 0. And you're just going to get 3. At this step, you might be able to stop here sometimes, but mostly what you're going to want to do is multiply this, whatever you get in this value, by whatever you get in this value. So 3 times 4 is 12. And yeah, this one was a pretty simple example, but you sometimes get binomials and trinomials times each other. So sometimes it's better to leave it in this factored form, this right here, or sometimes it's better to do what we did in this example right here, where this is a square root again. So as we talked about up here, you change from square root to the 1/2, as I did, as you can see, and then I applied the chain rule. And right here at this step, I got 6x plus 4 times 1/2. So sometimes you're not going to get numbers that look that pretty, where it's even numbers, so they split up perfectly into 3x plus 2. you might get 3.5x plus 2.5. Some cases it's better to leave it in its factored form, but in this case, it was just better to leave it like this. Perfect. Awesome. And the final derivative law that we're going to be dealing with in high school, believe it or not, is going to be power of a function rule. Oh, that's not my highlighter. There it is. Power of a function rule. Okay, so basically a power of a function rule, it's kind of the power rule, power law, but for whole functions. That's the way I view it in my head when I'm studying. So we're taking any function that's raised to the nth variable or nth exponent, and what we're doing is we're bringing it in front. You can see right here, bringing it in front, subtracting one just like we're doing power law, and then we're multiplying by the inside, whatever's in g of x prime. So the derivative of whatever's inside. And we'll look at this example right here. We have b of x is equal to x squared plus x to the 3/2. So this is a case where it's kind of, the numbers aren't so friendly. So we can't really, once we're done with bringing this, once we're done with bringing this in front, as we did here and took the derivative of what's inside, which ends up being right here, we don't really want to multiply these two together because it'll get a bit messy. So this is fine. We can leave it like this and we will still be able to get full marks. Of course, it's all dependent on what the question's asking. So it might ask, please state your answers in simplified or expanded. So please pay attention to whatever the question asks of you. And yeah, that'll conclude the first part of my first ever Zoom presentation. I hope I did okay. I don't know. This is my first time doing this. So thanks for watching, and I hope you come back for part 2.